We are going to start today, probably finish on chapter 14. Got a few more loose ends to tie up. Where I wanted to begin was on the subject of acetals and cyclic hemiacetals. You will recall from last time how we showed you the mechanism for acetal formation. And we said that there's an intermediate along the way, the aldehyde or ketone carbon attached to an OR group and an OH group, and that's called a hemiacetal. We said it's not generally a stable intermediate, and instead it goes on to form the acetal, or in the presence of water, often falls back apart to the aldehyde or ketone and the starting carbonyl compound. You're going to need a little bit of practice in recognizing hemiacetals. And along with that, you're going to need to recognize an exception to the idea that hemiacetals aren't stable. And that is that when you can form a ring, cyclic hemiacetals actually can be quite stable. So here is, let's see, 1, 2, 3, 4, 5. Here is an aldehyde that also has an alcohol in it. And under mildly acidic conditions, and even in water, so I'm just going to write mild aqueous acid. It turns out that this is the linear, what we would call the linear open chain aldehyde form, is in equilibrium with this 5-membered ring form. Make sure I got that right. 1, 2, 3, 4, 5. Yep. Now, a couple of things are happening, I imagine, in your brain when you see something like this. Number one is, what the heck just happened? Number two is, that molecule on the right is totally unrelated to the one on the left. How did that even get there? And number three is, if I asked you, what is the key functional group in this molecule? My guess is 50% of you are going to say it's an alcohol. You're not wrong, but you sort of are wrong, because it's not really just a regular alcohol, it's a hemiacetal. So you got to get good at pattern recognition in unfamiliar circumstances. This, what I've drawn here on the right, is a cyclic hemiacetal. Now, let me just show you something, and I've done this in office hours with a few of you, and it was interesting to see the lights go on when you realized what you were looking at, but I imagine this is a challenge for a lot of you. What changes when I draw the molecule like this? Is it easier for you to recognize this as a hemiacetal? No problem, right? Why is it harder here then? Probably because your brain is distracted by interesting but irrelevant details. Does it matter that this R group is tied back onto that R group? Not really. The chemistry doesn't change. Nevertheless, just in my experience, I've observed that students sometimes, when complexity is added to the molecule, sometimes they get distracted by that complexity in a way that causes them to forget what they already know. And maybe there's a life lesson in that too, but somehow in your practice, you've either got to learn to take this and redraw it and simplify it like this, or you have to learn to focus in on the key part of the molecule and relax your eyes on the other parts of the molecule. Maybe it'll help if I show you how we get this and how you can get from here to here. The strategy is to recognize that you've got an aldehyde, which is reactive, and an alcohol in the same molecule. And so this is an intramolecular reaction. Intramolecular reactions are generally faster than intermolecular reactions. We mentioned that briefly at the end of class last time. The reason for that is just in an intramolecular reaction, the two reactive partners don't have to swim around in solution until they find each other. They're already tied together. All right? So, what would happen here is you would expect the carbonyl oxygen to get protonated by your acid. That's the first step in acetal formation. That would give you the familiar oxonium ion. Notice what I'm doing. I'm relying on what I know about aldehyde chemistry. I'm also, I'm not worried about the alcohol oxygen. Some of you are thinking, well, can't the lone pairs on that oxygen get protonated too? Sure. Does that lead anywhere to a useful intermediate? No. And when we have aldehydes, the aldehydes are always the electrophiles. So it makes sense that we're first going to protonate the aldehyde to make it even more electrophilic, and then in a second step, the alcohol is going to come in and attack the carbonyl carbon to give you a tetrahedral intermediate. Now, the fact that the alcohol that does the attacking and the electrophile that gets attacked are attached to each other means that this is an intramolecular reaction and it's going to form a ring. We have a word for that in organic chemistry. A reaction that forms a ring is called an annulation because you make a ring, and that's sort of the Latin root for ring is annular, right? Annual, we go around the sun once a year in a circle. That's Spanish speakers. What is the word for a ring, like a ring on your finger? Anillo, right? Same basic root word, annulation. This is a ring-forming reaction. That term will come up again in the class, which is why I'm introducing it now. To know how to do this, and again, I recognize students struggle with this, so it's going to take some practice. Start with the atom that does the attacking and count until you reach the atom that gets attacked. Those are the number of atoms in the ring. Draw a polygon of that size, right? So now we're going to draw a 5-membered ring or a pentagon, and atom number 1 needs to be an oxygen. And there I screwed up and didn't draw it right, so we'll try again. There we go. That is a 5-membered ring containing oxygen. Go ahead and number the atoms of the ring, and then you're going to put all the key functional groups in the right place based on these numbers. For example, carbon 2 is a methylene group, CH2, so is carbon 3, so is carbon 4. Carbon 5 was the electrophile that got attacked. It has a hydrogen on it, and then it also should have an OH group on it. And there is your cyclic hemiacetal. Okay? Again, now if you started with the cyclic hemiacetal, how are you going to recognize that this is a hemiacetal? Look for the OH group and an OR group on the same carbon, and then recognize that that used to be the carbonyl carbon. How can you tell what kind of carbonyl it was? Look at the other two things attached to the carbonyl carbon. Are they both carbon, or is one carbon and one hydrogen? If they are both carbon, it will be a ketone. If one is carbon and one is hydrogen, it will be an aldehyde. Okay? This OH group was your nucleophile. This carbonyl oxygen becomes your OH group. Yes?
Shouldn't we have 2 OH groups?
Shouldn't we have 2 OH groups? Not in a hemiacetal. You're thinking of a hydrate, which we haven't talked about yet because it's easy.
I'm just saying we have 2 OH groups in the...
Oh, did I skip ahead? You don't like that, do you? Okay, well, fair enough. You are right that the alcohol that did the attacking should still have a proton on it. So let's show that. Sorry for skipping that step. Then, in the last step before we get the hemiacetal, the conjugate base of our acid will remove the proton. Sorry, we need red arrows. And that will get you to your cyclic hemiacetal. So yes, my apologies there. And can you handle that we flipped it over like that? You're mostly okay with that? Okay. I probably can't, but I'm going to do my best to ignore it. Yeah, go ahead.
What about your receiving fixture?
If you make a stereo center, yeah, you would expect to get both configurations. You're noticing that this is a stereo center, so you're right. Okay? Good. What else? How about, yeah, go ahead.
You can make acetals from ketones and aldehydes, right?
You can make acetals from ketones and aldehydes. Yep. In fact, we could have done that here, just replace the proton with the methyl group and keep it all the way through and keep everything else the same, and it works fine. Others? Yes?
If instead of 5 atoms long, it was like 6 or 7, would that increase its likelihood of forming a cyclic structure?
Good question. If it was 6 atoms long or 7, would that increase or decrease the likelihood of structure? That's an interesting question for a class that we teach, Chemistry 552. You can take it from my colleague Dan S. Nobody's ever taken us up on that, actually. But no, real people do take the class, just not generally. Anyway, so not generally people that don't have to, I think is what I meant to say. So no, the amount of hemiacetal formation would be related, among other things, to the stability of the ring. So you could imagine making a ring that's so small and strained that it's not very efficient. And you can also imagine making a ring that is so large that it's also not efficient, because the larger the ring, the longer it takes the two ends to find each other. 5, 6, 7 membered rings all form great. Okay, what else? Yep, if you made it with the ketone, just replace this hydrogen with a methyl group or something else and it would look the same. Okay, a couple more things on this. Let's go backwards because I know that is also a struggle for you. So now, behold, oh, the horror, a 6-membered ring hemiacetal. And I could ask you, again, in mild aqueous acid, this is going to be in equilibrium, so with an open chain form. So I could ask you, what is the correct open chain form of this cyclic hemiacetal? And to do that, again, how do you recognize that it's a cyclic hemiacetal? Well, look for the OH group. Look for the OR group, where the OR group is tied back to the same carbon that the OH group is on. The carbon that bears the OR and the OH used to be the carbonyl carbon. Then I look at the two other things there, and if they're both carbons, then that used to be a ketone. Importantly, I'm going to start from the oxygen. 1, 2, 3, 4, 5, 6. The blue carbon is going to be my carbonyl carbon. The pink OH group will be my carbonyl oxygen in the product, and the purple OR group is going to end up as the alcohol. So to draw this, what I'm going to do is I'm going to start with the oxygen, that's my OR group, the alcohol, and then I'm going to draw, this is atom 1, then 2, 3, 4, 5, 6. Did I get that right? Yeah, I think we did. 1, 2, 3, 4, 5, 6 atoms. Is that right?
I think you added a carbon in the ring from the last molecule.
I did. Yes, that was on purpose. Thank you, though. Yeah, I intended to do a 6-membered ring just to change things up. Yep, that's good. So so in purple is the oxygen. So the OR group becomes the alcohol. Carbon 6 should be my carbonyl carbon, and the pink oxygen should be my carbonyl oxygen. Carbon 5 is on one side of that, and then what I'm missing is this other methyl group, which is the ketone. All right, that's how you open up a cyclic hemiacetal. Practice that until it makes sense and until the fiery SpongeBob panic of doom in your brain. Did we talk about that last time? I'm not sure whether we did or not. Well, yeah. until you're able to suppress the panic response, okay? All right, we can make this worse. We can make this actually much worse. Before we do that, though, I should point out that even though cyclic hemiacetals are stable, you can take them on to the full, complete acetal, and there are examples of doing this in your textbook. Here's one, and here is the conditions. You have a hemiacetal as a starting material, and then you have a second alcohol. Now, notice that the starting material for hemiacetal formation only has one OH group in it, and that intramolecular reaction gives you the hemiacetal. But if we supply an acid catalyst, if we have an alcohol, and importantly, if we remove water, what we can do is complete the mechanism and move forward and form the acetal. Now, some of you looking at that, if you're struggling with pattern recognition, you're thinking this is just a simple, well, I gotta do a SN2 reaction where the alcohol kicks off the OH group. And that's exactly the wrong thing, because this is not an alcohol. This is a hemiacetal. What you're looking to do here is to complete the acetal formation. Now, just to review from our acetal formation mechanism, what we did when we were at the hemiacetal stage is we protonate the OH group. The OR group acts as a kicker-offer to kick off water as a leaving group. We remove the water, we have now an oxonium ion, and then the second alcohol comes in and attacks. Hopefully you've practiced that some so that that is familiar to you. If it's not, what does Alma 5 say? I would that such an one would prepare swiftly, for the day soon cometh when, whatever. So, get to work. So what we would do to complete the hemiacetal formation is lone pairs on the oxygen would pick up a proton from the acid. That would get us to this intermediate where this OR group is going to act as a kicker-offer and kick off the pink oxygen, which should be positively charged. Okay? That's going to generate an oxonium ion that looks like this. Again, if you're not good at pattern recognition yet, you're going to look at that and think, what the heck just happened? If you go back and compare what we drew in acetal formation, the only difference between this up here and this here is these OR groups are tied to each other. Okay? That's just your oxonium ion, which is now electrophilic enough for the alcohol, the second alcohol, to come in and attack, break the pi bond, get this intermediate, and then lastly, we will remove a proton, probably using the conjugate base of our acid catalyst. And that will get us here. Okay? All right. Now, the neat thing about all of this is this sets the stage for some beautiful things that we're going to do in a subsequent chapter later on in the course about carbohydrates. This is, I mentioned that it was possibly going to get worse, and so here is the worst part. You ready? You need a minute to finish copying that? Too bad, just download the notes, sorry. Oh, okay, fine, we'll wait. I needed a drink anyway. All right, let me draw a complicated cyclic hemiacetal. It's really very similar to what we've drawn here, except I'm going to draw it in its chair form, and this is a cyclic hemiacetal formed by glucose. This sort of ups the challenge. This molecule is called beta-D-glucopyranose. You won't need to know any of that until later. But, and if you looked at that, you might have been overwhelmed by all of the functional groups. You might not have been certain what to look at. You might not have known where to start. It's fine if you look at that and say, that's a chair, and I vaguely remember chairs being important in 351. Okay, that's a good start. Chairs are the conformations generally adopted by 6-membered rings. It's also fine if you look at that and say, there's a lot of OH groups. Analyzing that a little bit more, I can see that one is a primary OH group, and the others are on secondary carbons. But one of these OHs is different than the others. Which one is different from all the others? The one in the lower right. Okay, why is that one different? It's a hemiacetal. Good. You can see that now. Here's an OH group on the same carbon as an OR group. Could you tell me now, is that blue carbonyl carbon from an aldehyde or a ketone? Aldehyde, very good. You know that because the two things that are attached that are not the oxygens to that blue carbon are, one is a carbon, one's a hydrogen. So this is the cyclic hemiacetal form of glucose, which means there must be an open chain form that is an aldehyde. So let's draw that open chain form. I have literally put this question on an exam before, and people got it wrong. And then I have literally put nearly the same question on the final exam before, and people got it wrong. So I'm helping you to be wiser than your predecessors have been, all right? If we walk through it in the same way we just did, it won't be that bad. So as I said, let's start with the purple OR group. That's going to be the oxygen that was the nucleophile when we made the hemiacetal. And we're going to number around the ring 2, 3, 4, 5, and 6 until we get to that blue carbon. All right? And so we'll just do, and I'm just going to draw the arrows to what the open chain form should be. Let's now start with the OH group. It will be most convenient. Sure, that's fine. It'll be most convenient to put this OH group here, and then I'm just going to draw zigzags until we get to atom 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Oh, we're there. Good. Okay, so this is the thing that was the nucleophile. This is the carbonyl carbon. It should be an aldehyde. Here's the hydrogen of the aldehyde, and here's carbon 5. 1, 2, 3, 4, and 5. Okay, so that's part of the problem. The other thing, and most people are actually okay with that with some practice. What students struggle with now is basically a challenge to their ability to reason through molecules in 3 dimensions and keep track of stereochemistry. Because it's diabolical, isn't it? Because what we're calling carbons 2, 3, 4, 5, and 2, 3, 4, and 5 are all stereocenters, and nothing else. The only thing that changed in going from the cyclic hemiacetal form to the open chain form was this became an OH group and this became a carbonyl carbon. Stereochemistry didn't change any other place. So you actually have to go through and figure out what the right configuration is for each of these OH groups. That's kind of a challenge, all right? I found, just for me, it's easiest to go through this in a couple of ways. For example, first, before I attempt to draw in those stereo centers, I'll usually draw this out and know where I need to end up. But I will often keep the molecule, I'll often redraw the molecule in its open chain form, but I will keep everything in the same place. The only thing I will change is the bonds between the purple oxygen and the blue carbonyl carbon. See what I've done there? Everything else has stayed the same. And I haven't attempted to put the molecule around in sort of its zigzag shape. All right. The other thing that may be helpful to you at this stage is to put the hydrogens that were implied but not shown. That can help keep us straight, and that can help us remember where things are. All right. Also, it's good to keep a consistent numbering scheme. It really doesn't matter where you start numbering as long as you keep it consistent. All right, let's go through this pretty quickly. Carbon 5, from my perspective over here in this drawing, and just to pause, do you see where I got that from? Okay. Carbon 5 is got carbon 6 on the right and 4 on the left, and carbon 5 is at sort of a peak position. You can draw zigzags. Zigzags either have peaks or valleys. That is a peak, and this is a valley. We're going to make a distinction between carbons that are at peaks in a zigzag versus carbons that are at valleys. We all talking the same language here? Okay. So carbon 5 is at a peak when 6 is on the right and 4 is on the left. Now notice that when carbon 5 is at a peak, the OH group is coming out towards me. You see that? So over here in my drawing, I'm noticing a similar situation. Carbon 5 is similarly at a peak with 6 on the right and 4 on the left. To keep the stereochemistry consistent, then, this OH group, which was coming out towards me here, must also be coming out towards me here. That makes sense? So it should be a wedge or a dash? Wedge, perfect. Okay? Now, you can check that. What we've done is basically, by thinking through peak and valley, what's on the right, what's on the left, is it coming out of me or is it pointing away? We've basically dealt with assigning R or S without you knowing it. You can go back and actually, if you want, convince yourself by assigning R versus S at that stereo center and make sure that we've got it right there. That will take a little bit longer, and if you make a mistake, you'll get it wrong, which is not that informative of a statement. But if you can assign R and S correctly, you'll get the right answer. Okay? Let's do this again for carbon 4. Now, to do this accurately, you're going to have to do some imagining. This is my Newman projection I, and because it's early and we're tired and the class is turning us to the dark side, those are our Anakin Sith eyes. And if you're shouting, "I hate you" at me while I tell you that I have the high ground, that's fine. Okay, so notice that from our perspective in this corner, carbon 5, carbon 4 is at a peak or a valley? Valley, it's down relative to 5 and 3, right? 5 is on the right, 3 is on the left, and 4 is at a valley. From that perspective, from where we're sitting over here in the corner, is this OH group pointing towards us or away from us? Towards us, good. So over here, is that OH going to be a wedge or a dash? I heard some of you hedging. It's actually going to be a wedge because see how our drawing over here, 4 is similarly at a valley, 5 is on the right, 3 is on the left. OH pointing out at you has to be a wedge. Okay? We're going to make a similar determination here, but again, you've got to be a little bit careful on your three-dimensional reasoning because we'll just move the aniconi. We are still, we're stepping around sort of behind the molecule, looking at it from this perspective. From that perspective, 3 is at a peak, 4 would be on our right, 2 would be on our left, and again, 3 is at a peak. When 3 is at a peak, that OH group is pointing towards us. So again, we would put it here, okay? Lastly, we have to deal with carbon 2, which is kind of obnoxious and annoying and difficult to see. To do this, I'm going to erase this hydrogen, which is in place. We're going to put this label for carbon 5 here. Yeah. Okay. What's the best way to think through that? It actually works out just fine if you can. All right, hold on. This is carbon 2, and then this is. Ooh, I screwed up, didn't I? No, not yet. We're missing something. What am I missing on carbon 2? Look at what carbon 2 is drawn as in my drawing here. I'm missing a hydrogen and another CH2 and an OH, right? Okay. So let's just now stand, let's look at the molecule from where we are. We're going to bring our aniconi back around to the front. We're just going to stare at carbon 2 from this front perspective. Notice as we've drawn it here, 1 is on our right, 3 is on our left, and 2 is at a valley. And from that perspective, the hydrogen, the CH2 group is pointing back away from us. So we could summarize carbon 2 from a different perspective like this. We could say the H is sort of angled towards us and the CH2OH is angled away from us. This is carbon 3, this is carbon, 3, 2, and 1. Do you see that? You sort of agree with that? Questions? Yes?
Does it really matter whether something's equatorial or axial?
I mean, of course it matters up here whether it's equatorial or axial, but what we're trying to do is translate that relationship into wedges and dashes here. The equatorial group, this CH2OH group, is pointing away from us, so we're going to call it a wedge. And then by default, the proton has to be angled towards us because that's the only other place to put it. Yeah?
I think what he's asking though, is it an oversimplification to just say that the equatorial stuff is going to be coming at us and the axial is going to be going away?
Is it an oversimplification to say equatorial is coming at you and axial is going away? Probably, because it depends on which way you're looking at it. For carbons 5, 4, and 3, we wound our way around the ring to look at it. For carbon 2, we're again coming back in front and looking straight at it. Yes?
So, and I guess that was my question, is I thought if it is, I guess, pointed away from us, but then the ring flips around and curves around, would it be the opposite?
We're going to deal with that later. Yeah, so your question is, now that we're looking at carbon 3 from our perspective straight in front, just getting an idea of the stereochemistry, how are we going to deal with swinging it around? We're going to do that in a second. Yeah?
Are we going to get models in the exams?
You can use models on the exams, yes. If you don't practice ahead of time, it will not help you as much as you think. Yep, others? Yeah. We haven't drawn that CH2OH or the proton on carbon 2. Others? Yeah.
I thought it was where, like, for the 3, it's equatorial down, so it's down.
So for 3, yeah, so you can, the question that you're asking, is it up or down, equatorial up versus equatorial down, works best when you draw the molecule from above like this, which you could do. So here is the cyclic hemiacetal form. Sorry, I drew this kind of quickly and the penmanship is poor. We don't have time to go fix it, so I'm going to ignore it. This is the correct overhead drawing of the chair form. So you were asking, is if something's equatorial or axial, is it up versus down? That question works best if you draw the molecule from overhead. What I've been showing you is how to go straight from this sideways chair drawing to this. Now that we've spent like 10 minutes going through it, I'm just realizing that it would have been better to draw it overhead first and then do it. So there's multiple ways to do this. And if you want, we can go through it real quickly from this perspective after we finish here. Yes? You guys cared so much once I told you I'd put an exam question on this before. Suddenly you like really care. This is good. Okay, I want to just come back to where we were. I'm showing you there's often multiple ways to solve a problem. We're going to take whatever time it takes to do this. Here is carbon 2. Oxygen 1 is on our right. Carbon 3 is on our left. 2 is at a valley. From this perspective, yes, the hydrogen is pointing down and this methyl group is angled up but away from us. But we have to try to translate this into this kind of drawing where this is in the plane of the page, this is in the plane of the page. That CH2OH group is angled away from us, so the only conclusion we can make is that this proton is tilted towards us. In effect, what you're doing is you're reaching back to carbon 2 and twisting it forward just a little bit. All right, so this is the drawing that you would get. Now, coming up here, where am I going to put the CH2OH group? Do you notice that carbon 3 up here is on my right, not on my left? Do you notice that the OH group here is on my left, not on my right? So the proton, which was a wedge, must therefore be a what? Dash. Now, an important point we made, though, is that 2 is still at a valley, right? So yeah, the proton must still be a dash, and the CH2OH group must be a wedge. Okay, that would be the correct molecule. A lot of the time, people don't like to put the carbon here as a wedge. They want it to be in the plane of the page. So we could actually redraw this molecule like this. 6, 5, 4, 3, 2. Here's the CH2OH group. Okay, so what we've done in getting to this CH2OH group is we have rotated around this carbon-carbon bond. The CH2OH group, which was in the front, we have swung around and tilted. We've swung around this way so that it's in the plane of the page. That's going to bring the proton on carbon 2 out towards us, and that's going to bring the OH group back into the plane of the page. So this is atom 1, all right? Yes?
Could our linear molecule be in some sort of equilibrium with a 7?
Great question, yeah. So one of the things you're noticing is if I choose, what if I wanted this to be my nucleophile? Is that what you're asking? What if this was 1, 2, 3, 4, 5, 6, 7 to the aldehyde? Yeah, you would expect it to be in equilibrium where the ratio between those two products would be related to the stability of the ring. It turns out the 6-member ring is more stable than the 7-member ring. So even though you've got that alternative for glucose, we only really ever observe the 6-member ring. You could ask the exact same question about the OH group on this carbon. Could we make a 5-membered ring? And the answer is yes, but again, 5-membered rings are a little bit more strained than 6-membered rings. Okay, others? Okay, one more thing, we probably should go through it pretty quickly because I'm just burning time on exam questions, which I guess is the whole point, isn't it? Let's start, and I really can't handle that. That's bad. So we'll try again. An alternative way to do this that may be easier for you to see, aside from building a model, is to put your evil Anakin eye up above the ring and draw the ring as it would appear from above. And when you do this, you learn this in 351, so we don't have a lot of time to go through this. Number the ring however you choose. I'm going to start with the oxygen that was the nucleophile. That's maybe not the most sensible thing to do. Groups that are up in our chair drawing, either up axial or up equatorial, are wedges. Groups that are down, either down axial or down equatorial, are dashes. So OH on carbon 5 is a dash, OH on carbon 4 is a wedge, OH on carbon 3 is a dash, CH2OH group on carbon 2 is a wedge. If you're not sure or if that's not making sense, you need to come back to this and go through it slowly and review. We don't have time to do that right now. All right. Then you do what I suggested and do the opening. Only keep everything in exactly the same place. So again, here's your OR group, here's the carbonyl carbon, here's the OH group. Keep everything else the same, only carbon, what we've called 6, is now an aldehyde. But again, everything else stays in exactly the same place with exactly the same stereochemical relationship. Then you're going to go through one by one and do this same analysis. You're going to ask, carbon 5 is at a valley, 6 is on the left, 4 is on the right, and OH is a wedge, is a dash. So we're going to come up here and check our drawing. In our drawing up here, 5 is at a peak when 6 is on the right and 4 is on the left. So the OH, which was a wedge, dash down here, must be a wedge there. Do you see that? Okay, you can go through, we don't have time for this, I'm really sorry. You can go through one by one all of these and make that same determination. The one thing maybe I will do for you, the most difficult stereocenter in the molecule is this one. What is easiest to do if what we did before didn't make a lot of sense is to simply, in your mind, rotate around this bond between 2 and 3 by tipping the CH2OH group into the plane of the page and redraw the molecule. If you do that, the new molecule looks like this. The OH1, which used to be in the plane of the page, now gets tipped out towards us. And then everything else about the molecule stays the same. If you do that and then use the tools that I've showed you, you should be able to come up with the same correct stereochemistry at that last carbon. Okay, that is a whirlwind, and I know you are scared. Your fear, I feel like a Sith Lord here. Your fear gives you power. Use it to motivate yourself to study, okay? Practice that a few times. For fun, if you want, for fun, right? You don't have enough to do in your life. Here is an exercise. This is an alternative sugar. It's called mannose. And yep, I've drawn it correctly. The OH that's axial is in the sort of front. So go ahead and draw, I'm not saying do it right now, but in your notes, go ahead and draw the open chain form and see if you can get it right. I will put the answer. I will remind myself. I will likely forget, but then one of you will email me and then I'll re-upload better notes. And then the answer will be there. Okay, that's more time than I really intended to spend on that. And you got 5 minutes to finish all of chapter 14. So, are you ready? Because we're hooking the hose up to the fire hydrant and we're about ready to go. One thing to remember is that you can do something very similar to acetal formation with just water. And that is you can form an aldehyde hydrate or a ketone hydrate. Here's a simple ketone. Here is the ketone hydrate and the aldehyde hydrate. Hopefully you've read about this in your text. You can actually make hydrates under either acid catalyzed conditions, that is using H3O plus and water, or you can do a hydrate formation under basic conditions, that is using H2O and OH minus. Under basic conditions, OH minus attacks the carbonyl carbon to give you a tetrahedral intermediate, and then the negatively charged oxygen gets protonated by water. Under acid catalyzed conditions, you protonate first to get the oxonium ion, and then water attacks, and you get a final proton transfer to get the hydrate. These are equilibrium reactions. The hydrate is always in equilibrium with the ketone starting material. Usually the amount of hydrate formed is small, and the amount of hydrate formed is a measure for how electrophilic a carbonyl carbon is. So that's kind of interesting. You would expect that the ketone would form less hydrate than the aldehyde because the ketone's less electrophilic than the aldehyde. So there's a question on your problem set that says which of these should have the highest percent hydrate formation. That's really a question about which carbonyl compound is most electron poor to begin with. So that should help you reason through that. Hydrates are not really useful as synthetic intermediates or protecting groups, so I don't really have that much more to say about them. Let's see, one other reaction that we did not speak about yet, but which is in your text and is in your study guide, is called cyanohydrin formation. This involves starting with an aldehyde or a ketone, using CN- as a nucleophile, and then you usually need some kind of acid catalyst. Your text says HCl. In practice, people don't generally do that. The reason for that is you don't want to protonate CN- because if you do, you make HCN, hydrogen cyanide gas, which is toxic. If you can smell the almonds, you're probably already dead. So it's sort of a dangerous reaction. Instead, what people do is they use a proton source that's not that acidic. Likely what has to happen, your text shows a mechanism that's probably a little bit different than I will show. What I'm doing is adapting the mechanism I showed for imine formation. Likely the cyanide nucleophile attacks as you're breaking the pi bond, as you're removing a proton from whatever acid proton source you have. And the product you make is this. It's called a cyanohydrin. Do you see the relationship between the cyanohydrin and everything we've done so far with making imines and hemiacetals? The pattern is you have a carbon that used to be the carbonyl carbon, you got an OH group, and then in purple you have the nucleophile that was attacking. And then the other two things are, well, the groups that are left over from the aldehyde. That's the pattern. Cyanohydrins that's a fairly simple reaction, but the reason your text introduces them here is later in chapter 16, we're going to learn that if you use acid and heat, you can actually hydrolyze that cyano group into a carboxylic acid, and this is an alpha hydroxy acid, which is a useful synthetic intermediate. So in any case, That's cyanohydrin formation. Now, there are two more things from chapter 13 that we didn't get to today. We have to do it next time. And those two things are the Wittig reaction and reductive amination. It will, we're not going to spend a lot of time on either of these, but you should make sure that you spend a little bit of time reviewing the Wittig reaction before class on Monday. Okay, see you then.